this recording. Okay, so everyone can hear me, right? I will begin the class now. And just testing, 1, 2, 3. Just checking the sound level. Okay, so we will continue where we left off on the previous class, which was about the circular motion, right? So we have derived, just before we finished our class on last Wednesday, we have derived the acceleration for an object moving in a uniform circular motion, right? Remember, we are talking about uniform circular motion where the speed is constant. And when the speed is constant, the direction keep on changing. We have managed to derive the magnitude of the acceleration. Here I call this the radial acceleration is equal to the v squared divided by the radius of the circular motion. And this is the magnitude of the centripetal acceleration. And sometimes you see the textbook, they call it centripetal, or sometimes they call it radial. Okay, it means the same thing. We have calculated the magnitude. Okay, so the next thing we want to figure out is what is the direction. So to get the direction, right, we recall that the acceleration vector is, well, it is the limit where dv dt goes to 0. So that means the direction of the acceleration vector is proportional to the change in the velocity, right? And then we take the limit where this delta v goes to 0. So how do we get the direction?
So I forgot to share your screen.
Oh, sorry.
Yeah.
Did I? Oh. Okay, can you see my screen now? Can, right? Okay, I'm sharing.
Yes.
Okay, I'm sorry. So now you can see. Yeah, sorry. I thought I shared, but I forgot. So yeah, so let me repeat since I forgot to share. Just now we were calculating our. In the previous class, we were trying to calculate the uniform circular motion, where the speed is constant. And in the previous class, we have calculated that the magnitude of the acceleration is given by v squared divided by r. So that is what we did just before we finished our previous class. Then now what we want to do now is to figure out the direction. So how to get the direction? So to get the direction, we remember that the acceleration is proportional to the change in velocity, right? So change in velocity means dv dt, and then we take the delta t going to 0, so it is related to the infinitesimal change at every instant. So let's get the change in velocity. All right, so let's look at the scenario. Initially the object was here, and then if it's moving a circular motion, later it was here, right? Same diagram I draw in the previous class. And to calculate the change, we use our vector method, right? So this vector, to figure out the change, we join the tail. So this v2, I can move it something like this over here. Okay, and then this is v2, right? It is equivalent if we move it in place, especially in R3 and R2. So the change in velocity is v2 minus v1, am I right? So the v2 minus v1 is this vector over here. So this is my delta v. Okay, so if I take the limit where my delta t is approaching 0, so notice that if my delta t approaching 0, these two vectors will get closer and closer to each other, and this vector is pointing more and more towards the center of the circle, right? So if I take a larger interval, the direction is somewhere like this. So if I take a smaller interval, right? If I take a smaller interval, this will be closer to this initial vector over here, and then you can imagine that this vector, in the limit where delta phi and delta t going to 0, this vector will start to point towards the center. So the instantaneous acceleration vector will be pointing towards the center of the circle. Okay, are you convinced? Okay, so hopefully this is you agree with this. We can prove this more rigorously if we express the parametric equations in of the circular motion, but that one we will probably do in the tutorial or something. Okay, but for now we shall remember that the direction of uniform circular motion, the acceleration is direction is towards the center of the circle. Okay, so that is the direction, and then we got the magnitude. So let me check everything is okay. Okay, looks okay. Right, so that is the direction. So we have determined the acceleration of the centripetal acceleration. So to summarize, our centripetal radial acceleration, right? It is a vector. So it's a vector. We can say its magnitude is equals to b squared over r, and the direction is towards the center of the circle. Okay, so that is the centripetal acceleration. Okay, so yeah, everyone follow so far? Okay, pretty straightforward, right? These are the basic things. Now, related to this, let us introduce some more quantities. This is just to introduce the quantity. We will use this more in the later chapters, but since we are here, we can introduce now, so that when we go to the later chapter, you are not bombarded with so many things suddenly. Firstly is we talk about the period of the motion. So this is a uniform circular motion, right? So every time it's going in a circle, right? 1 round, 2 round, 3 round, 4 round, keeps on going. So what we can calculate is sometimes we care about how long does it take to go 1 round. So this is the time taken to complete 1 round. Okay, so time taken to complete 1 round, we can calculate because we can use the relation that since this is speed, right? So speed will be given in some meters per second, and we can calculate the circumference of this circle. So that will give you the length. So if I divide this with the, that means the circumference of one circle over the time taken to cover that circumference should be equal to the speed, right? This is a constant speed. So just take the whole thing divided by the total time. So from here we get 2 pi r, and then the period, usually we call this the capital T, the symbol, and then the speed we have been using is just the v. So the period is just 2 pi r divided by v. Okay, so this is the time taken to complete one circle. So this is one period. Okay, so for any distance, how many meters divided by how many meters per second, you can determine the time it takes. So related to the period is the frequency. Okay, so a frequency is the inverse of the period, basically. Sometimes we call it f, and it's defined to be 1 over t. So basically it's just v over 2 pi r. Okay, so sometimes people call this f. If you see some other textbook, right, they call this frequency with this symbol, the Greek letter nu. I don't know how to pronounce it, so this is called nu. It's not v, but I don't want to use this often because it looks like v, so we don't want to confuse it with the real v. Okay, so this is the Greek letter nu. Looks like this, but we will use f, so it's more straightforward. And so anyway, that's the frequency, and then we will be encountering this, especially when we talk about rotation, the angular frequency. Okay, so the angular frequency is just 2 pi times the frequency. So we have omega is equals to 2 pi times the f. And since f is 1 over t, so you got 2 pi over the period, right? And since the period is also v squared over 2r, we can actually calculate even further. So it's 2 pi v, right, over 2 pi r. So we got the relation that v is equals to r omega. Okay, so this is a formula that relates angular frequency to the speed of your circular motion. Okay, so this one again, we will use this a lot in your in the rotation chapter later. So it's a good time to get to know it as in the early stage, so that you'll be familiar by the time we need to use it. Okay, so this is the this is our uniform circular motion. Okay, so let me emphasize one more thing, because this is important. Is a just a re-emphasis of things that I already said. Is that when we talk about a uniform circular motion, right? Okay, so we have object. This time, just for variety, let me draw the object moving in an anti-clockwise direction. Okay, so if I'm going at a constant speed v, the speed is constant, but we have a velocity vector, and the velocity vector is not a constant, right? Because it keeps on pointing in different directions. And we notice, this is the emphasis I want to have. The observation here is that we have calculated the radial acceleration, which is pointing towards the center of the circle. So notice that my velocity vector and my radial acceleration vector is perpendicular to each other. Okay, so the property of a uniform circular motion is that my velocity vector is always, well, it is tangent to the circle. That is also another thing, right? Velocity vector is always tangent to the path of what you are moving. And it is also perpendicular to the acceleration vector, which we call the radial acceleration. Okay, so this is a thing. And again, if we actually write the parametric equation of this motion, we can actually prove this. And I'll do this later. Okay, so that one will be more involving a bit more formulas and calculation. It's straightforward, nothing complicated, but just some more calculations only. Okay, so that is the uniform circular motion. So my acceleration vector points to the center, my velocity vector points to this, and they are perpendicular to each other. Okay, this is also important. Just to give a preview of why I mentioned this, right, is that if for an object moving in uniform circular motion, the force that causes it to go in a uniform circular motion will do zero work. When we come to that, we will discuss this a bit more later. Okay, so it's going to do zero work, and the reason is because it's 90 degrees. Okay, so that is uniform circular motion. Now, uniform circular motion is just a special case, right? In general, your objects moving in a circle may or may not move at constant speed. You can speed up or slow down. So this is where we start talking about non-uniform circular motion. Okay, so non-uniform. Okay, let me double check. Still recording. Still recording. Okay, so this time the recording doesn't stop. Test. Okay. Test. Okay, so let's continue. Non-uniform circular motion. Okay, so let me draw a circle again. It is another circular motion, but this time the speed is not constant. Okay, so the speed is not constant. So let me explain what I'm doing. This is a circular motion, but this time speed is not constant. Okay, so that means if I were to draw the circle again, okay, right, so this is my center, and let's say is moving in a circle, but let's say at some instant the object happens to be here, so the radius of the circle is r, right, and then the velocity vector is this, but this time the magnitude may not be the same all the time. It may change. Okay, so it may change. Now if the object is moving in a circular motion, right, there's still going to be a radial acceleration. Okay, so it's going to be a radial acceleration over here, a radial, like this. Okay, if this is not moving at a constant speed, then I will have another acceleration. Okay, so if you think about it, right, for uniform circular motion, okay, this is a changing velocity, and the reason why the velocity changing is because of this radial acceleration. Okay, so radial acceleration will cause the object to change direction, but the speed maintains the same. Okay, so the same thing follows here. If I have a radial acceleration over here, it will cause the object to move in a circular motion, right? But it is not capable of changing the speed. So if the speed is changing, there must be another acceleration that causes the speed to change, right? So there must be another acceleration that causes speed to change. And because it's only changing speed, we just want a new, the changing direction already settled for this term. We want the new acceleration, we want it to change the speed only. No need change direction, already settled there, right? Only change the speed. So if I only want to change the speed, then the direction of my acceleration vector can be parallel to the velocity vector. Okay, it could be backward, then it was slowing down the speed, right? If it's forward, it will speed up the speed. Okay, so this is my new acceleration, so we call this the tangential acceleration. So for a non-uniform circular motion, I have two accelerations here, right? So this one will cause it to go in a circle. Fine, we done that just now. This one will cause it to change the speed. If this term is 0, then the speed will be constant. Okay, so I have two acceleration here. Therefore, there's going to be you can calculate a total acceleration vector. Then it's going to be having some direction over here. Okay, so you can use the vector sum to calculate the total. Okay, so to summarize what I was explaining here, let me write in a more technical language. Total acceleration has two components. Okay, so the total acceleration has two components. So we have this one and the tangential acceleration. Okay, so for this term, we have already learned how to calculate already. It's a vector, so you can say its magnitude and direction. So magnitude is v squared over r, the direction towards the center. And then for this, for this, firstly the direction, it will be what's the word? Proportional to v. Do you know why I chose the word proportional and not same as v? Just to remind you, right? It could be same as v, right, pointing the same way, but it could be also pointing backward, right? So it is a scalar multiple of v, to be more precise, right? Okay, the scalar multiple, this scalar could be a positive number or negative number. Okay, then magnitude. Well, it depends on how v changes, right? So magnitude is, we can actually calculate this. So the magnitude is, well, we can calculate the magnitude A tangential is just the rate of change of the speed. Or if you are given this, we can just calculate this like this. Okay, so you can calculate using this formula. And of course, it depends on the situation. Sometimes the v changes a lot, so you get a higher tangential acceleration. Sometimes the v changes very little, so you get a smaller tangential acceleration. Then you just need to calculate based on the situation. Okay. Everyone follow so far? Follow, right? Okay, no questions. Still recording? Yes. Okay. So I guess now to see how everything works, let us work out an example. Anyone? No copying, right? So let's try to solve this example. So this is example 1.5.1. Okay, so to show you this, okay, example 1.5.1. So we have a particle moving in a circular motion of this radius. So 2 meters initially is at point A. So point A is over here. And then the speed is 3 meters per second. And then 0.1 seconds later, it is at point B with this. Okay. Then the magnitude of tangential acceleration is constant. So based on this information, we are able to determine this magnitude. So we can solve part A, and then we can calculate the radial acceleration at A and B respectively, and then we can sketch the vectors when it is at point B. And then we need to do all these things. Okay, so let's do that. Okay, so skip. Then yeah, I'm still not used to all the different settings. So let's try to solve this problem. 1.5.1. So okay, let me experiment a little bit. So let me bring this to the front. Move to top. And then so that we can have a interesting situation that that you can see the question and I solve it at the same time. And hopefully it doesn't block the screen too much. Okay. Huh? Okay, so I think this is better. I don't know, or maybe like this is better. Okay, how about this? Then visualizer. Okay. Okay. This one put back. Okay, looks good. Oh, cool. Okay. So, oh, it's blocking. It's blocking a bit. So usually my hand is at the bottom of the screen, right? So let me swap with my face. And then what was this? Yeah. I think now it's okay now. Oops. Okay. Yeah, this is cool. I like this. Okay. So let's try to solve this, right? As I discussed just now, as the question said just now, the tangential acceleration is, the magnitude is constant. Okay, so since this is constant, we can use the kinematic equation. The constant A kinematic equation. The equation that we derive in the end of the very first class, right? Which is just V is equals to the initial V plus AT. Okay, so for this problem, initially it is point A at 0.3 meters per second, and then at point B it is 5 meters per second. So the final velocity is, let's take V to be the final, and then 3.0, and we can use this information to calculate my A tangential. So which is A tangential is just minus and divide, you will get 20 meters per second square. Okay, so that is how you get the tangential acceleration. Okay, then the next part is we want to calculate the radial acceleration at points A and B respectively. So that is very simple. The radial acceleration is simply given by this formula, which is just V squared over R. So that means at point A, right, my radial acceleration is just use my velocity at point A. My velocity at point A was 3 meters per second square, and then the radius of the circular motion is just 2 meters. So if you divide, you get 4.5 meters per second square. And then at point B, my radial acceleration, just use the value at point B. So you got 12.5 meters per second square. So one thing to notice is that for a non-uniform circular motion, my radial acceleration magnitude is no longer a constant, because it depends on V squared over R. For non-uniform, the V keeps changing, so the A is V squared over R, so the magnitude itself is keep on changing. But the direction is still pointing towards the center of the circle. Okay, so the reason is because, yeah, it's changing, so this vector will grow depending on how the velocity vector changes. Okay, and then you get this situation. So this is a non-uniform circular motion. Then for part C, we want to sketch. Okay, so let's try to sketch the vectors when everything is at point B. So let's draw part C. Right, so we're going to sketch. So point B is somewhere here, right? So my B is, let's say my B is here. Okay, and then my sketch the vectors A radial and A tangential and determine the total acceleration. So this is an increasing velocity. We have got the magnitude, and since this is an increasing speed, then the tangential acceleration is going this way, right? So this is my A tangential. The radial acceleration is always pointing towards the center. So from my vector summation method, I draw the parallelogram. In this case, just a square. So this is my total acceleration vector. So I sketched this already. Okay, so that is my vectors and my acceleration vector. So that was part C, and to part D is to find the angle between A total and A tangential. So A tangential, A total is over here. So this is this angle. Okay, so how to get this angle? Well, this is just a triangle, right? Just now we got this, so we can use our triangle method. The length of this vector was 20. Okay, and then the length of this vector was what was it? When it's at point B, right? So it's 12.5. Okay, so it's 12.5. So that means what is this angle over here? Okay, so from here, 12.5, right? Do you agree that tangent theta is equals to 12.5 divided by 20? Am I right? Okay, not Yeah, correct. So that means the inverse tangent to get the answer is just arc tangent 12.5 over 20. So this is 32 degrees. Okay. You know what I mean when I say this, right? Some people use this. Okay, so that's how you deal with non-uniform circular motion. Actually, the questions are very simple. They just need to, usually it's complicated because of the words. The question read in long sentences, and based on the sentence, you need to figure out what is the situation, what is initial, what is final, what is the A radial. And if you're able to do all that, then the calculation is just more or less like that only. Nothing complicated. Right? The complicated part is usually to, from the words, they write the long words, and then you need to understand in terms of the equation. Okay? So, yeah, so that is circular motion. Everyone okay so far? Let's check. Any question? Everyone okay? Okay. Yes? What? Which one? Oh, you mean moving this way? Can, but the you get the same answer. Yeah. You know why, right? Because the initial velocity, initial speed, final speed, even if you do it the other way around, you get the same answer everywhere. And it is also the reason why it's the same is interesting because for the online people, there's a question is that can we assume right that the particle is moving the other way around? The answer is yes, because the question just gives you the values only. Even if you assume the other way around, you get the same answer, right? The angle between these two is still the angle between these two. And the reason why it doesn't matter is because we look at the picture, right? Like from this picture over here, right? But imagine if I stand behind this piece of paper, then it's moving the other way around, right? So it depends on where you're standing also. Okay, so in the mathematical language is just the orientation symmetry that you flip. Okay. Yeah. Usually from now on, right? Usually my habit is to instinctively draw anti-clockwise because if you follow the Cartesian coordinate, your angle starts from x-axis and then you increase, so it's in the clockwise direction. So now everything is still okay lah. But later, right? The direction, even though you assume it's not important, but when we come to the rotation problem, if you have multiple objects, right? If you assume one convention, then you must be consistent. Otherwise, you mix up and then you get the wrong answer. So yeah, must be careful. Even though now it's okay, right? But when we come to rotation, must be careful. Any other question? Okay. So yeah, so that's it for circular motion. And again, this is just kinematics. So this is the easy part. We are introducing it under kinematics and nothing complicated yet. The hard part comes when we go to chapters, the rotation chapter. That is, in our experience, usually is everyone's most hated chapter. The one about angular momentum. Yeah, rotation, rolling with slipping. Yeah, because it's very non-intuitive, and
not like as linear as we think.
Yeah, linear is okay for everyone, right? Because it's intuitive. Like we see linear things we move in everyday life, and then rotation, even though there are rotating things in everyday life, we don't really we don't really pay attention to it, right? That's why some of the results are surprising. Okay, so we will come to that when we go to that chapter. So the next thing, okay, what time are we now? Okay, am I still recording? Yes. Hang on. I'm still recording. Voice is okay. Yes. So the next thing we want to talk about is the relative motion. Wait, I don't need this. Here. Relative motion. Okay. So this is 1.6. We are talking about relative motion. So just for fun, who has heard about relativity before? Einstein's theory of relativity.
Never before.
Okay, good. That means allow you. Yeah. That means okay. I like it because it is my research area. Right. We're gonna be talking about this later, and it all starts from this, the relative motion. Right now, for today, we only learn the basic one, the Galilean relativity. Okay. So but towards the end of this course, we will start to talk about the special relativity. So yes, time and things like that. Okay. So the reason why this is interesting is because you just start with something very simple, and then if we follow the simple logic, but if we go further and further, then we get some very, very strange result, very, very surprising. And even though it's very surprising, but people actually done the experiment for relativity and things like that, and then it turns out to be true. Okay, so what are we talking about? Relative motion is, the thing to remember about relative motion is that for us, right, when we're doing physics, we use our variable x, y, z, right, and then the time t as a parameter. Okay, so x, y, z is a Cartesian coordinate, right? So Cartesian coordinate is a particular reference frame. It must be some reference frame. That means the origin is a certain place. Okay, so so the origin is a certain place, but even though it's a certain place, it is not actually very physical. It's just something you purposely choose for yourself. Okay, so so whatever physical phenomena happen, right, it should not care who you choose to be the zero of your coordinate system, right? For example, GPS coordinate. Let me see if I remember correct. So GPS coordinate, the zero latitude is where? Greenwich, right? Greenwich. I believe it's spelled like Greenwich, but it's pronounced as Greenwich. Yeah, if you ask a person from British person, he will say Greenwich. Greenwich Mean Time and things like that, right? So that means the 000 coordinate for our GPS system is in Greenwich, right? It's in England, somewhere in England. Why is it in England? Because the person who invented this is probably a British person, right? So it just choose his home to be the standard. Okay, but physical phenomena, if you airplane doesn't care who is the home of this guy, right? So it shouldn't matter. That means we should keep two things in mind, right? If we calculate this thing, if we calculate some quantity, it is based on some coordinate system. So if a different person use a different coordinate system, then it will be different. Okay, so imagine if someone from Malaysia invented the GPS, the mapping system, then the 00 coordinate would be like in Kuala Lumpur or something, right? Right. So it depends. So that means the numbers, GPS numbers, will be different, but the actual location should be the same, right? So this is what we're talking about when we talk about different coordinate systems. So that one is fine, right? Different coordinate system. But things become more and more complicated if your coordinate system are moving relative to each other. That is the relativity. Okay. So have you sat on a train before, right? You sat on a train and then waiting for the train to start moving, and then you're waiting very long, very boring, and then you see out the window, and then suddenly you see out the window, right? The train next to you start to move, and then you move already, but actually you are not moving. It looks like it's actually the next train that is moving, right? So it's a perception type of problem, right? So that is the one of the many things that we will address if we are able to understand the relative motion. Okay, so so this is the motivation why we want to do all this. But now let us try to actually solve. So let us start with a scenario just to follow. Another situation is this, more probably something we have experienced before. If you're driving a car, right, and you want to overtake another car. So let's say you are inside car A, and this car is moving at 10 meters per second, okay, moving in a positive x direction. I take positive to my right, and you want to overtake another car that is moving very slowly. So let's say this car is moving at 7 meters per second. Okay, so if you drive at this speed and this car is driving at this speed, what do you see, right? So if you're inside the car A, right, you will see car B. Because you are faster than B, car B will be moving closer and closer to you, as long as you're going faster. But relative to you, the car B will be moving towards you at 3 meters per second. Okay, so what I'm trying to say is car A sees B moving towards A. At 3 meters per second, it should be -3, right? It's coming this way. Huh?
B already towards A, still -3. Already have a direction moving towards. So it's still -3, then it's moving up away from.
So correct. So that means I can just take out this, right?
Yes.
Yeah. So car B moving at 3 meters per second, and I'm going to give this notation. So this is the velocity of B as observed by A. Right? So velocity. So this means of B as observed by A. Okay. So car B is moving towards you at 3 meters per second. Now imagine you are the car B, right? You are the one driving slow. Okay. So some guy driving so fast coming behind you. That means it is moving towards you at +3. So car B sees A moving towards B at +3 meters per second. And this is what we will call this, because since this is car B seeing A, right? So this is the velocity of A as seen by car B. Okay. So that is the basic. Can you see? So this is the basic situation over here, right? In the lecture notes, I put 10 and 5, but I think if I put 7, it's more clear who is the difference, right? So 10 minus 5 is still 5. So, but in any two speeds, you are able to calculate. Okay. So now, actually, when I say 10 and 7, right, I sort of did not specify something, right? So this one is measured with what coordinate system, right? It's relative. I should specify now. It should be relative to the ground, right? So when you drive, what you read, your speedometer is relative to the road, right? So that means VA and VB is velocities relative to the ground. So we should say that this is relative to the ground. Okay, and then from here, what we conclude that how do we calculate this number? Okay, so how do we calculate this number? To calculate VB observed by A, right? We actually take this minus this, so you get -3, right? So it's coming to you. So this is actually VB relative to the ground minus VA relative to the ground. And then similarly, how do we calculate VAB? VAB is VA to ground minus VB to ground. So from these two expressions, and from here also we can already see we have the formula that VBA, if I swap these two, is just negative VAB. Okay, so if you change perspective, then you see the other direction. Okay, so this is the basic setup. right? So the basic setup starting from our everyday experience. So now we want to do it in a more mathematical or technical way, so that once we have a formula, we can apply to any situation. So what we're going to do next is to try to express this in terms of coordinate system. So for at least for this course, in our chapter, most of the time we will be dealing with 3 coordinate systems. Okay, so the first two is this. So we are going to let A and B carry their own coordinate system. Okay, so what does this mean is that, where's my, so that means A has their own coordinate system, x, y, and then B has their own coordinate system. Okay, so we carry their own coordinate system. That means for the position of A under its own coordinate system, we put it at 0, origin. Okay, this is an origin for B. Now, once you have the coordinate system, right, these are coordinate system that is moving relative to each other. So in this case, right, for this course, we will be most of the time studying the coordinate system that is moving at constant speed relative to each other only. So this is what we call inertial frames. Okay, so inertial frames are coordinate systems that move at constant velocity Okay, so this is what we mean when we talk about inertial frames. So I think for now, I will move this to the back. Is what in the notes? Inertial frames. Did I forget to put it in? Okay, let me add them in later. Okay, very hidden. So I should put it in a more obvious way. Okay. Any other question? Okay, everyone's okay, right? Test. Okay. So where were we? So inertial frames are coordinate systems that move at constant velocity. Yeah, I should write it in its own paragraph. Then it's more clear. So let me change that. Okay. So now let us describe our basic setup. Okay. To describe this basic setup, as sort of what we have described already, right? A is seeing B move at a certain speed, right? So, and we have called this speed the velocity of B relative to A. And again, as I mentioned, since I mentioned just now, but let me write it out to be concrete. Let A and B be at the origins of their own coordinate system. And then another thing also, to make our calculation more simple, at time equals to 0, A and B are at the same position. Okay, so at A and B are at the same position. That means, what does this mean? So if at time 0 they are the same position, but B is moving away from A at VBA, so at some later time that is greater than 0 later, where is the origin of B? So the origin of B is at distance well, VBA times t away from the origin of A. Does that make sense? It will be clearer if we draw pictures. So let me draw the origin of coordinate system of A. So this is the origin for A. So car A is always there. Okay. And then let's say car B is in a different place, right? So car B is, so initially car B is in the same place at time 0, but as time goes on, it's moving away. So this is the origin of B. Okay. So from this, so from here we can calculate this distance, right? So what is this distance? So this distance is VBA times t. So when time t is equal to 0, they're at the same place. But as t increases, it will be further and further away. Here I draw it such that VBA is positive, right? If VBA is negative, then it will go the other way. But anyway, the distance between the two is like this. Okay. Now, this is still very simple. But in order to solve more complicated questions, right, we need a third object. So let's say, right, the scenario that I want to do now is this. So I have car B and then a car A. They are both driving at different speeds. And then both of us are observing something else. So both of us are observing a bird flying at a certain speed. Okay. So the velocity of the bird that you measure will be different of the velocity of the bird that the other car measure because they're moving at different speed, right? So let's say we are observing a third object. So this third object, I will call this P. Okay. So relative to car B, right? Then this is the position of the point in the B coordinate system. Okay. But also this is the position of this bird in the A coordinate system will be some other number because you are using different coordinate systems. But you can actually relate the two because from here to here, right, we notice that we can actually get this distance. So what is this distance? This length is the same as this length, so it's xpb, right? So, and then what is this full length? This full length is xpa. That means we can get the relation between the two. So, so from here we conclude that xpa is equals to, well, it's this length plus this length. So it's xpb plus vbat. Okay, so this is the method for any point, for any coordinate system. We can transform one coordinate system into another. So this is a coordinate transformation. So this is a particular coordinate transformation which we call a Galilean. Okay, so we call this Galilean because this is named after Galileo, the Italian astronomer. Before the time of Newton, he already started to consider this already. Okay, so this is the Galilean transformation.
Nothing in Newton. Gravity, everything else.
Okay, so to now, position actually for most of the time, right, is this one is how to get a position. So what is the next thing? We want to get the velocity. Okay, so once we got this, it's very simple to get velocity. We just need to differentiate. Okay, so if I differentiate both sides of the equation, dxpa with respect to t, differentiating dxpb with respect to t, and then remember we are saying that inertial frames, right? Inertial frames velocity constant. So if you differentiate this constant, so the t just disappears, so you got VBA. Okay, so this one is just basically just the velocity of P as observed by A. This is the velocity of P as observed by B, and then this is VBA. Okay, So this one is the Galilean transformation for velocities. And for this chapter, we will be using this formula quite often. Okay? Okay, so everyone follow so far? So if everyone follow, we shall be solving this example. Yes? You mean in the notes? Don't have, man?
I think our notes is like previous version.
Oh, I did update. Lah. I think I got add this like a couple of weeks ago. And in fact, the example this one I just added it last week. So, but yeah. By the way, I should also tell you, I'll be updating the notes throughout the course. If I find typos or, if I want to add more examples. Okay. Okay, actually, since this is 11 already, so let us take a break for around 5 minutes. Then, when we come back, we will apply what we just learned to the example. Okay, online people, are you okay? Okay. Okay, so see you in 5 minutes. I will stop the recording and stop the OBS recording. So yeah, in 11:05 we come back. Record. Test. Okay, good. So let's solve this question. Okay, so can read from here. I hope it's not too small. This example is about a car driving north. You are driving north in a road at constant 88 kilometers per hour. The truck on the other lane approaches you at 104 kilometers per hour. So we can treat this as a one-dimensional problem, okay? And then we just need to calculate the truck's velocity relative to you, your velocity relative to the truck, and whether they change after you pass each other. So if it's too small, I will just draw it here, okay? The truck, okay, is coming down, and then you, I'll just say you lah. Okay, so come here, and we shall follow the picture provided in this question, which is we are taking the x-axis positive upwards to be here. So how do we solve this problem? We will be using our relative velocity formula quite often. So let me keep this somewhere convenient. So we got VPA, and then VP observed by B plus VB observed by A. So basically, normally we have three things here: A, B, and the point P, right? So A is some coordinate system, B is another coordinate system that is moving relative to A. So to solve this question, right, I find that the best way is to assign who will play the role of A, B, and P for this question. So what I'm going to do is, for this part, well, for part A, I want to find the truck's velocity relative to U. So let me assign U to be the coordinate system A, and then the truck to be coordinate system B. Okay. Sorry, the truck will be, since we are observing the truck, right, we shall take P to be my truck. Okay. And then when we say that the car is 88 kilometers per hour, as I mentioned just now at the beginning, this is the velocity relative to the ground. So the ground is another thing here, and we shall take this to be my B coordinate system. Okay? So actually you can assign it in different ways. You should be able to get the correct answer anyway. just that you just put in the signs correctly. Right? So if you are, according to the question, 88 means what? 88 is relative to the ground, which is to say that the V of A relative to something is 88. So which one? B. Right? So this is how you put this here. Okay. Then the truck is the point P, and it's moving downwards at 104 kilometers per hour. So this should be relative to the ground as well. Okay, so this is how you set up the question. You see who is A, who is B, who is P, and then you put in the variables correctly. Now that you have decided this correctly, then we can use the relative velocity formula. Okay, so the relative velocity formula is what we just derived, right? VPA is equals to VPB plus VBA. Okay, and then we have, well, VPA is the truck relative to U, which is what you want to calculate. And VPB was, we got this to be minus 104. And VBA was, 88. Hang on. 88 relative to the ground plus, wait, is there a mistake somewhere? Oh, okay. Now I see what's wrong. We said that VB 88, but what we want is VBA, not VAB. So this is negative VBA. Yeah, this is very easy to forget, so I just forgot just now. So it's negative. So that means I want the opposite of this. Correct? And you can imagine, right? Is if one person going at 88, the other direction plus 104, the result will be even a larger speed. So the final result is negative 192 kilometers per hour. Okay. So this is the velocity of the truck relative to U. So that's why car accident, right? Head-on collision is more damaging than two cars colliding in the same direction, right? Because the speed add up, so you crash faster. Yes.
I will ask for the maybe for coordinate system like different direction.
Yeah.
Is it, for example, here is positive, and here is the position heading. Is it counted like this or still counted like this? Means like for the.
So for this, we are the same.
Means like the positive in the same direction.
Yes.
So relative to the truck, if for this question relative to the truck, so it will be the negative of the velocity relative to you.
Yes.
Okay.
You can actually do it both ways. You can, but usually we yeah. So let me repeat the question. Like so you're asking that the car A is moving at, taking this as positive, right? And then the truck is coming in the other direction. So do we put it this way or this way, right? Usually, to make your life easier, we just put everyone in the same direction. Okay? But if you do it this way, also can, but you need to remember to switch back the sign when you do the calculation. The reason is because this formula we were deriving assuming everyone point the same direction. Okay? Yeah? So yeah, yeah, just to make your life easier, just take everyone to be the same direction. Therefore, the truck is moving at the negative direction according to himself, right? But everything should still get the same answer. Okay, so that is yeah. Let's talk about B first and discuss the further implications next. So the next thing is to find your velocity relative to the truck. So from the perspective of the truck, how are you moving? So since we are talking about the velocity measured by the truck, we can say truck should be A now. And then U is something that is observed. So let's put U as the P. and then ground can be B. Okay, so these two can change the role, it's fine. You will get the correct answer as long as you put in the numbers correctly. So the velocity, okay, so for this case, the velocity of the truck relative to the ground will be minus 104 kilometers per hour. Okay, and then the velocity of u relative to the truck, don't know, but u relative to the ground was given to be 88, positive 88 kilometers per hour. Okay, and then using the formula again, so VPA is equal to VPB plus VBA. Okay, so VPB was 88, and then VBA was, this is AB is 104, so I flip the sign, so it becomes positive 104, right? So you still get 192 kilometers per hour. But this is just, I'm just showing you how to plug in the formula. But if you understand the question, you already know it should be the negative sign of this answer, so it's positive 192. Right? You see the truck coming at 192, so the truck will see you coming at negative of the previous answer. But I'm just showing you this to show how to plug in, because again, question will be more and more complicated later, and just by imagination it might be not so clear, but if it's not clear, you just plug in the formula correctly, you still get the correct answer. Okay, final one is just a simple concept question. How do the relative velocity change when the truck pass each other? It doesn't change, right? So relative velocities do not change. Because notice that our calculation, right, we did not assume where is the positions of the truck. The truck could have been already passed, where we did not put in the position anywhere. Okay, so our calculations did not depend on position. Okay, specifically calculations A and B. Okay, so what was I wanting to say just now? Yeah, I forgot what I wanted to say. Never mind. Okay, so that was the example. Okay, yes. Part C. Because part C, right? How to say? So the answer is the same. That means, right, even after the truck, so I'm going to explain part C again. So even after the truck and car pass each other, what is the velocity of the truck observed by you after you already pass each other? It is still negative 192, right? So if you see this picture, right, you are seeing the truck coming to you at 192 downwards kilometer per hour. But even after you pass each other, the truck is still going this way at 192 kilometer per hour, right? Agree, right? Yeah, so it's the same answer. Before you pass or after you pass? Yes, yes. So the lesson from part C is the position and velocity, they are different things. Right? Velocity is still velocity, so it's still the same. Okay, any other question? Okay, so if not, we go to the next thing, which is to, well, what we have been doing just now was to study our relative velocity, everything assuming one direction only. So we're going to do 2D and 3D now. So we're going to talk about relative velocity. In 2D and 3D. Okay. So we draw the same picture. How do we study this? So now we include vertical directions and x, y, z directions, everything. So, but it's still the same situation because object A will still have the origin. Okay, so this is the origin as according to A. And then we have another object that is carrying its own coordinate system. So this is B. So let's say B is having its own coordinate system. So this is the origin of B, right? But this time, I don't care about just the x direction, but I also want to know what is the y direction and maybe the z direction as well. So to describe the position of B relative to A, we use the position vector. Okay, so the position vector, so over here, this is the position of B as observed by A. Is it clear if I draw it like this? Okay, so from here, right, it's still the same thing. Okay, same situation. That means A and B own coordinate system. Right, and then B, so the origin of B is moving at the velocity of B observed by A relative to origin of A. Okay. Then at time 0, we assume they are the same place. So at time 0, OB is the same place as OA. So at any future time, okay, the position of the origin of B as observed by A is constant speed, right? Inertial frames. So we have V BA times T. Okay, constant speed kinematic equation. Great. Yeah, I'm recording, right? I'm recording. Okay, good. Clear so far? Okay, so pretty straightforward here. So what we're going to do is to just to repeat the same thing, but this time in vector form. Okay, so let's say both of us are observing another object. So let's say my object here is over here, so that I can write the vector more clearly. So this is the, let's say I have an object P. So from the perspective of B, this is the position of P as observed by B, right? And from the perspective of A, this is the P as seen by A. So notice that we have drawn a closed triangle, right? We got a triangle. Is basically this vector RPA, and then we have RBA, and then another triangle RPB. So this is like a vector sum where this is the resultant vector. So from here we can conclude that this form a triangle. So we RPA vector is the vector sum of these two. So we got RBA plus RPB. Okay, so let me move to this picture. Right? So this is the Galilean transformation for 2D and 3D. Because this is vector, it could be now contain x, y, z direction. So now that we got this, then we can differentiate both sides again. So the derivative of RPA dt, and then the differentiating RBA dt. And then because this one it was equals to R just now, right? RBA with respect to t. So if I differentiate this with time, I just end up with VBA. Right? So this one is basically just the velocity of P using the A coordinate system. This is the velocity of B using, hang on, I used the wrong symbol. P observed by B. P observed by B. Yeah, sorry, P observed by B. And then V, B, A. Okay, so this is the transformation for the vector form, right? It's basically, actually it's exactly the same as this, but you just add the arrow on top. Easy to remember, right? Yeah, question?
For the acceleration.
Uh-huh.
I was wondering, like, if we, because from this example, I just like from this proof,
Yeah.
I feel like if we just put the A replaced with the B, we still can do the same thing, right? But we just calculating, we just draw a triangle with what the acceleration as a component.
Yes.
Then relatively for the position, for this example, then the position S of like the coordinate position after at the function of t.
Yeah.
Means like it's the velocity at the function of t at the acceleration component.
Yeah. So basically your question is, if you want to handle acceleration, just do not assume these v's are constant. You can still differentiate them anyway.
Yeah, so it's like only one more level, like.
Correct. Actually what you say is correct. Yeah. Actually what you say is correct. If you are just purely talking about coordinate system, so yes, you can transform accelerating coordinate system in the same way for inertial frames. Although the problem is the laws of physics, if you transform the coordinate system, they will change. Okay, so let's think about this. So why can't we use the coordinate system? So if you're talking about Newton's law, right? So you got F is equals to ma. Okay, so ma is dx dt, so dr dt. Okay, so if you for the inertial frames, right? If you change your coordinate system, so if I use a new coordinate system, okay, using f prime, then I need to convert. I'm supposed to differentiate this using the new coordinate system, right?
Yes.
So if I'm talking about inertial frames,
Both coordinate systems almost the same.
yes. So r prime is going to be something plus something. Okay, so let's say r. What's the okay? It's the original r, and then plus the vt. Right?
Okay.
So if v is constant, second derivative, this term will disappear.
Yes.
Right? So then my f prime, so if I change my coordinate system, I'm still going to get dr dt.
Yeah, exactly.
Okay? But if this is not a constant, I will get something here.
So something like a change of variable.
Yes. So the Newton's law do not remain the same between different coordinate systems. Yeah. And we can still like continue with the story lah. Okay, you can still continue this. This is something, that means this is something like an extra force.
Yes, it is.
Right? So what's the term? Yeah, so this one is like people call it the virtual force or things like that, right? Or Coriolis force. That will happen. Okay, so you will change the laws of physics, but you can, even though you can continue the calculation, but the Newton law is no longer the same. Yeah, so that is the reason why we focus on inertial frames only. Okay. Okay. So so we are focusing on inertial frames only. This will be the velocity transformation, where all the velocities are the same. So let's do the example. Okay, so the typical type of question that we will encounter is something like this. we have an airplane with a compass heading due north, airspeed indicator showing that it's moving through the air at this speed, and then there's a wind. So there's most of the time there's always three things, right? So that it become A, B, and P. So the three things in this question is the airplane, the wind, and the ground. So that is how we shall handle this. Okay, so let's do a new page. Okay, let me open this. So we are in example 1.6.2. Okay, so we have the airplane going north, and then the airspeed going this, and then there's a wind blowing over the earth. So for this type of question, how do you handle this? Again, we shall assign who to be A, B, and P. So for this question, we will take our coordinate system to follow the north, south, east, west. So my positive x is the east, my positive y is the north direction. And then I can decide my plane to be point P, okay, and then my wind to be B, and my earth to be A. Okay, so based on this question, right, how do we solve? Well, let's look at this information. Where is it? Okay, so the airspeed indicator shows that the plane is moving through the air at 240 kilometers per hour. So let me write this clearly. So you guys are not familiar with this type of question, right? So I go in more detail. I will go more slowly in more detail. Airplane is moving through air at 240 kilometers per hour. So airplane is moving through the air. That means this is relative to B. So which is to say that my velocity of my plane relative to B, well, most of the time it will give you the speed. So we know the speed only. So this is 240 kilometers per hour. Okay, so my airplane is moving through the air at this one. Then what is my second statement? The wind is 100 kilometers per hour from east to west. So there's a wind is blowing at 100 kilometers per hour from west to east. So I can write the full vector, right? Because this is the velocity of the wind relative to the ground. So from west to east is positive x direction. So this is 100 kilometers per hour in the x direction. Oh yeah, airplane compass is headed due north. So the direction is due north. Actually I can write the full vector here also. Okay. So what happens is that you have an airplane, right? Usually for this type of question, the airplane can control its direction and speed relative to the wind, but the wind can blow it away in a different direction. Okay, so the compass and the airspeed will tell you the velocity of the plane relative to the wind. So now that you have this both information, right, what is the velocity of airplane relative to the earth? So which is the velocity of P relative to the earth. So using our formula, okay, which is just VPB plus VBA. So just plug in the information that you have. You have 240, and then VBA is 100, but in the I direction. So this is X component and Y component. So basically our answer is 100I plus 240J kilometers per hour. Okay, so that is VPA. Okay. Then the next part is in what direction should the pilot head in order to travel north, right? So that is that is the problem that people encounter if you are flying a plane. You can control your plane relative to the wind only. So you can aim your airplane in a certain direction. You can try to go there. But if there's a wind blowing against your plane, then you end up going in a different direction, right? So if you just want to, so if there's a wind blowing from your side, right? If you've been blowing coming to your side, but if you want to go straight, right? You point your plane straight, but the wind will blow you off. So in order to make sure you really go straight, you must adjust your plane this way. You adjust your plane this way, you will tend to fly this way, but your wind will push it back. So if you adjust in the correct angle and the correct orientation, then you can perfectly move straight. So that is the situation that we have here. So that means we need to control our VPB so that the actual motion is moving pure north relative to the Earth. So that is what we want to do. Okay. So to just now after what I said, let me write this down here. What we want is velocity of plane relative to ground is north, which means that only have the J component. Okay, and what we can control is the direction of plane relative to ground. And according to this, we are assuming constant speed, right? Assuming 240 kilometers per hour. So we can control this. So if we can control this, that means if we keep a constant speed, we can change our direction. So we can say that, okay, it is moving at 240 degrees. In the horizontal component, we can resolve cosine theta, and then 240 degrees sine alpha in the J direction. Follow so far? Right? We can control our alpha, our angle. Okay? So, sorry, I keep using the wrong, relative to the wind. Yeah. So what we want is VPA to be moving purely north. Okay, so that means VPA is VPB as always, and then this is the wind speed. So this is the wind relative to the Earth. So what we have now is, well, the first term is 240 cos alpha I plus 240 sine alpha j, and then the wind speed was just 100 I. Right, so I got the x and y components over here. So I can combine the two together. So basically I have 240 cos alpha plus 100. So this is the I component, and the j component is 240 sine alpha in the j component. Okay, so this is how we want to solve. If I want my velocity to be only north, only j component, that means this must be 0. Okay, so how do we make this 0? That means cos alpha is minus 100 and 240, which gives me the alpha 115 degrees. Okay, so my plane should be flying in at this angle. Okay, so what is the direction? So we just need to say the direction, right? So we are using the Cartesian coordinate system. So 115 degrees is this way, VPB. So we have calculated this to be 115. Okay. So how to say? This is west, right? So 90 minus 115 is what? 25. Correct? 25 degrees. So the answer is direction is 25 degrees west of north, correct? Right, so this one will clearly say that you are going in this direction. Okay. So what is the plane velocity relative to Earth? That means we just need to calculate VPA, right? So VPA is just, well, we have calculated this already, right? So it's 0I plus 240. Sine alpha, we have calculated alpha to be 115 degrees in the j direction. So if you compute the answer, it's going to be 218 j kilometers per hour. This one is very simple. Okay. Is there any question? Okay, still recording. OBS is still recording. Okay. So next example. So next thing is we're talking about is 1.6.3. Yeah, so this one is the new example I recently added. And in this example, we have in this picture a plane moves east while the pilot points the plane somewhat south of east. Oops, I typo wrongly. Towards a steady wind that blows northeast. Okay, so we got the information about the wind blowing northeast. The plane is roughly going south of east, right? So in the east direction, but a bit south. So at a certain unknown angle at the moment. Okay, so the plane has velocity 215 kilometers per hour relative to the wind, then directed at the angle. So the wind has velocity this relative to the ground. So we have to find theta. So for this question, we can say that the ground is taking the role of A, and then the wind. The question sometimes already assign you the symbol. So we just call wind to be the object B, and then P should be our plane. Okay. So according to the information, right, the plane moves due east, but the pilot was pointing the plane somewhat south of east. So that will tell me the velocity of the plane relative to the ground. Hang on. Okay. So plane points due east, moves due east, while the pilot points the plane somewhat down. So we got this picture over here, right? So north, south, east, west. So the plane is, let's say this angle is some theta, right? This is the plane pointing somewhat south or east. So this is the velocity of the plane relative to B. Am I right? Okay, so yeah, sometimes it's a bit tricky and must be careful to get everything correctly, right? So the speed is 15. So the speed is 215, and from here I can get my x and y component. So this is 215 cos theta I, then is minus 215 sine theta j, correct? This component is downwards. Okay, so this is the velocity relative to the wind. And then the wind, right? The wind itself is blows northeast.
Do you have enough information?
Hang on. Huh? Wait. So I think it's not enough information because I think I'm missing a sentence. The wind was blowing 20 degrees here. Yeah, I'm sorry. When I typed this example, I forget to the velocity of wind with respect to ground. So let me edit here. Okay. So the velocity of wind relative to ground is this. So it is this sentence is gone. So this is 65 sine 20 degrees I plus 65 cos 20 degrees j. Okay. So this is given, which I forgot to give. So later I'm going to update this lecture notes. Yeah. So I'm sorry. So we got this information, and then from here we can find out what is theta. Okay. So we shall use our formula. So Vp relative to the ground is it is Vp with respect to the wind, and then plus V, the wind relative to the ground. So from here we got 215 cos theta I minus 215 sine theta j, and then wind relative to ground is 65 sine 20, and then 65, this is I, 65 cos 20 j. Okay, so based on this information, the question says that the plane only moves due east. Which is to say that there is no j component. Okay, so that means this term is 0. Okay, hang on, no, I forgot. So these two terms added together is 0. So I got 215 sine theta plus 65 cos 20 degrees is equals to 0. So from here we got sine theta is equals to 65 cos 20 over 215. So this is what I calculated was 0.2841. So the angle is 16.5 degrees. Okay. Okay. Yeah, so sorry, the question is incomplete. I will update this in the lecture notes, but then this will be the answer to the full question. Okay. So everyone is okay here? Looks okay, right? Yes. So that is how you solve all these questions related to relative velocity, right? Just need to assign who is A, who is B, and who is P, and then you apply the formula accordingly. So yeah, and so that is our last topic for kinematics. So the next thing we can move on to is now chapter 2. We start talking about the Newton's laws of motion. Okay. Any question before we move on? No? So now we go to Newton's laws of motion. Okay. As I said at the beginning, kinematics is about describing the motion of object, right? Velocity, position, how to get one given the other. Right now, so kinematics is actually not really physics yet. So now is the physics part, is why the object move, how it move. So this is where we start to learn about Newton's laws of motion. Okay. So yeah, so in this chapter we shall be talking about Newton's laws. So this is chapter 2. Not much time left. So yeah, I'll just talk, right? Just talk. Yeah, because if I start a calculation, it will take much longer. So in chapter 2, right, we'll be learning about Newton's laws of motion. And this one is most of the time is being already taught in the high school. There are 3 laws of motion, right? And it is named after Isaac Newton. So he formulated these laws in around 1652 or something, that kind of year. I forgot exactly the year already. And the story of where he formulated is actually kind of relevant to us now, because I don't know if you know the story, right? At that time, Isaac Newton was a university student. And then he got the same situation as us. At that time, there was a pandemic. I think it's called epidemic. Epidemic is within one country. So in England, there was an epidemic, the bubonic plague, right? So same situation as us. The university closed down. All the students go home, right? But luckily, at that time, Isaac Newton no need to do online class. So he's very free at home, right? So he's very free at home, and he's free to continue study by himself and do all the experiment. And eventually, he came up with the 3 laws that we are learning now, and also the gravitational law that we learned in the later chapter.
And calculus.
And also, he invented calculus. Yeah. So in order to formulate this law, he need to invent calculus, right? And then ultimately, everything that he have learned, he written down in the book Principia. So
That's why I said our pandemic is different from Newton's pandemic.
yeah, Newton got no online class.
Pandemic, we like, damn, my pandemic.
Yes. So but his pandemic quarantine was like more than 2 years, I think. So he got plenty of time lah, right? So for us, we quarantine for like 6 months only, and then
I feel like even in pandemic, I still play phones. Oh fuck.
yeah. So he got no phone, he got no games. That's why he can do all this kind of thing. Yeah, or online class, you know, that kind of situation. So yeah, so I don't have time to go through the details to start this topic now, but on Wednesday class we will start to learn about this Newton's laws of motion. Okay, and maybe at the second hour of Wednesday, I will do some tutorial question. And also, don't worry, I will upload the solution for everything much later after we've gone through the tutorial. Okay, so yeah, so I think that is as much as we can cover for today. Everyone okay here? Online? So if everyone is okay, we shall end the class. And let me stop the recording here. So stop the OBS.